All right, so this is the first of several lessons working with something called absolute value. And in its essence, absolute value is very simple. What we'll find is that it gets more challenging and a little more intricate when it's applied in different situations. But absolute value, as it says here, is essentially the distance of a number to 0, or a distance from 0 to a number. And since I say it's a distance, it's always positive. Distances are always considered to be positive. And so if we look at the symbol for absolute value are a type of bracket, these vertical lines. They are a type of bracket, so they do affect the order of operation. But everything inside those brackets represents the distance from 0, which again, it probably sounds more complex than it is in reality. But again, that phrase absolute value and these special brackets are equivalent. So let's look at this. This is we say the absolute value of 3, which essentially means how far is 3 from 0? 3. That's it. So -7, the absolute value of -7, we can think of how far from 0 is -7. 7 units. And so what we notice is that essentially absolute value just makes everything positive, the output of the entire what's inside the brackets. And so like I said, in many ways it's extremely simple. So the absolute value of -2 plus 1, now we don't want to now go, okay, well that negative becomes positive, because no, they are brackets. So order of operations, first I need to think about what -2 plus 1 is. And -2 plus 1 is -1. And now I think about the absolute value of -1, which is how far is -1 from 0, which is just 1. So again, a common mistake is to think now, okay, anytime I see these brackets, anything that's negative inside it, I make positive. But no, again, they are brackets, order of operations, I have to perform the operations inside the brackets first. All right, and so for these next three, as long as we follow our order of operations correctly, this should be rather easy. If we're going to make a mistake, it's probably not performing our order of operations properly. So here I have the absolute value of 4 minus the absolute value of -6. Well, first, the absolute value of 4 is 4, and the absolute value of -6 is 6. So now it's 4 take away 6, which is -2. Over here, first, let's think what's inside the brackets. 2 minus 7 is -5. So I have the absolute value of -5 times 3, all being subtracted from 5. Okay, next, let's find the absolute value of -5. The absolute value of -5 is +5. So this is the same as 5 minus 3 times +5. And now if this is just like basic order of operations, this is 5 minus 15, so it's -10. And the last one. A lot of stuff going on, but really the key thing to realize is that everything we see here is inside the absolute value. So the very last thing I'm going to be dealing with is the effect of that absolute value. So order of operations, 5 minus 7 is -2. So I have -2 times -2 squared. I'll just do all of this together. -2 times -2 squared is the same as -2 times 4, which is -8. -8 plus 6 is -2. And now finally, the absolute value of -2 is +2. So again, these are brackets. They work, they affect the order of operations. It's like any other bracket. But the main difference is that everything inside it eventually becomes positive. If everything inside it already is positive, these brackets are just no different than any other bracket. And that can be kind of summarized like this, something called piecewise form. And what you see here is a definition of the absolute value of a number, but written in piecewise form. Okay, so let me say a few more things about that. This is probably your first introduction to equations being expressed this way. Essentially, when you see an equation expressed like this, and notice I say the absolute value of A equals, and then I see two different things. These are two different pieces. And these are defining what this absolute value of A does, depending on these restrictions. And so the way you read this is, if you look at what's highlighted in yellow, the absolute value of A is the exact same thing as just A, which means those brackets do nothing, if A is greater than or equal to 0. So if A is essentially a positive number, those brackets do nothing. And that's what I've kind of already mentioned. If, however, A is a negative number, then the absolute value of a is the same as minus a, which you can think of it as -1 times a, which maybe sounds backwards at first because I've said if something is negative, absolute value makes it positive, but that's what this is doing. If a is a negative number, let's say a is -2, well, if I want to algebraically change the sign of -2 to make it +2, I can multiply this by -1 to get +2. And so putting a negative in front of a variable is essentially equivalent to multiplying by -1, and multiplying any number by -1 changes the sign. And so this here is a sort of more algebraic definition of absolute value. So with that said, let's define these two functions in piecewise form. So here I have x plus 2 instead of just a. Well, if you look at what I have up above, the only difference is everywhere there was an a, there's now an x plus 2. And so let me literally write this in piecewise form, just like I said. So the absolute value of x plus 2 is going to be x plus 2, which means those brackets will do nothing as long as x plus 2 is greater than or equal to 0. Again, not just x is greater than or equal to 0, x plus 2, everything inside the brackets. And again, these brackets will do something. They will change the sign of x plus 2, which means the whole thing is going to be multiplied by -1 as long as x plus 2 is less than 0. If anything seems strange here, just notice compared to what I have up above. And again, the only difference, and I've been trying to highlight this with my highlighter, is that every single time there was just an a up there, there's now x plus 2. So I can definitely clean this up a bit. So this is not in simplest form. For example, if I just write this, and again, I have to write these two pieces. My first piece, x plus 2, is fine. But this restriction of x plus 2 is greater than or equal to 0 is a little bit needlessly complex. If I just subtract 2 from both sides of this inequality, it's easier for me to say where x is greater than or equal to -2. That really makes it nice and explicit when I look at this piece. If x is a number greater than -2 or equal to -2, I look at this first piece. Otherwise, look at the second piece. And I can distribute the negative, and maybe, sure, why not? I'll distribute the negative, although that really is a matter of, that's not essential. But again, what is essential is to make this restriction really, really easy to read. Isolate the x. And so if x is less than -2. And so what we have there is the equation of the absolute value of x plus 2 expressed in piecewise form and simplified. And again, I now know, if I'm looking at this, if x is any number greater than or equal to -2, I look at this piece here, which means whatever x is, I'm going to add 2 to it. However, if x is any number less than -2, then I look at this piece right here. And this also gives me a sense about what the graph of the absolute value of x plus 2 looks like. If I think about the graph of y equals x plus 2, I can start to get a sense because realizing it'll be these two pieces. They're both lines, but they're different lines. One line has a positive slope, one line has a negative slope, one line has a y-intercept of 2, one line has a y-intercept of -2. So if we look in piecewise form, I can start to get a sense about what the graph of the absolute value of x plus 2 looks like. However, that's not actually essentially part of today's lesson, so I'll leave that for now. That's leading into the next lesson. All right, so similarly, I want to express this in piecewise form. So again, I'm going to do the exact same thing as before. I'm going to think of my basic definition of piecewise form and, absolute value in piecewise form, but instead of an a, I'm going to have 2 minus x. Okay, but again, I can clean this up. And again, all I did is substituted everything where there was an a above with 2 minus x, exactly like that. But now, to clean this up, it's about my restrictions that are needlessly messy. The 2 minus x, and if I distribute the negative, this is the same as x minus 2. That's not a big deal. Or -2 plus x. But I want to isolate x here. And so I will say if I subtract 2 from both sides, that's a good start. But what I have is this. I have negative x is greater than or equal to -2. Or I have negative x is less than -2. And while that's not wrong, that's hard to understand. I don't want to isolate negative x. I want to isolate x. So I have two options. I could swap around these terms. However, again, even then, it's a little bit needlessly difficult to understand. For example, if I have this, x is any number less than 4, or if I say 4 is any number is bigger than x, they mean the same thing. But if I ask you to pick a number less than 4, you can probably come up with that way faster than if I said pick a number that 4 is greater than. They mean the same thing. But if I said pick a number less than 4, I'm sure you'd have one in an instant. If I said pick a number that 4 is greater than, you have to do a little logic puzzle in your head for a second. It's still not hard, but it's needlessly more complex. And I don't want things to be needlessly complex. So what I want to do here is I want to multiply both sides by -1. However, one thing you may not realize is that when you multiply both sides an inequality by a negative number, or if you divide both sides an inequality by a negative number, you need to flip around that inequality. So if I'm going to do that, which I want to do, my inequality will be positive x is less than or equal to positive 2, and x minus 2, where positive x is greater than positive 2. That is the simplest form of this. My pieces are very, very clear. If x is less than or equal to 2, I look at the top piece. If x is more than 2, I look at the bottom piece. That's it. I don't have to do any little logic puzzles in my head. But this idea of me having to reverse my inequalities or flip them around because I multiply by or divide by -1 is something that you may not be aware of. It's pretty easy to explain though. If I just pick two numbers, 2 and 3, 2 is clearly less than 3. If I add a number to both of them, it'll still come up with an inequality that's correct. 3 is less than 4. If I divide both sides by a positive number, I don't know, 2, divide both sides by 2, I still come up with an inequality that's correct. 1.5 is less than 2, which is everything, all that's correct. No matter what I do to both sides, no matter what operation I do to both sides, my inequality will be correct unless I multiply or divide by a negative number. So notice, if I take this here, if I multiply both sides by -2, and I don't change my inequality, I get -3 on one side and I get +4 on the other. Oh, sorry, I should be multiplying both sides by the same thing. So I get -4 on the other. And now this statement is false. -3 is not less than -4. So to make it true, I have to reverse the inequality. And again, essentially, anytime you're dealing with an inequality, as long as you're not multiplying or dividing both sides by a negative number, you can deal with it just like any other equation with your 4 basic operations. All right, so with that said, this final problem is again a lead into the next lesson, and thinking about what happens to a graph of a function if you find the absolute value of it. So first, for this, f of x is x squared minus 4. So I want to eventually think about what does the graph of the absolute value of f of x look like. Well, first, let's think about f of x. And again, I don't need a table of values to sketch f of x. I know what f of x looks like. For example, I know from our quadratics unit, it's exact same as x squared, but translated 4 units down. So I'm going to visualize this in blue. My vertex is down here, 4 units down. I know I go 1 over 1 up, 2 over 4 up, 3 over 9 up from my vertex, and it's symmetrical. And that's my graph of f of x. And every single point I just plotted connects conveniently enough to this table. -3, comma, +5, -2, comma, 0, -1, comma, -3, and so on. All right, so that's, again, f of x. So now, what I want to think about, what's the graph of the absolute value of f of x going to look like? Well, if I compare these together, these two tables have the same x values. The only difference is this is the absolute value of this. And so I just need to look at my y values in the table and find the absolute value of them. So for example, here I have a 5. The absolute value of 5 is 5. The absolute value of 0 is 0. As in, again, if absolute value is a non-negative number, it's not really doing anything. If absolute value, if f of x is -3, now this is where something's going to change. The absolute value of -3 is +3. It's going to be +4, +3. So these 3 were the only negative outputs I had here. These are the only negative y values I put on my table. So these are the only numbers that actually changed when I find the absolute value of them. And then these don't change again. OK, so what does, again, the absolute value of f of x look like? A table doesn't tell me exactly what it looks like. A table can give me a good sense and to kind of get a feeling for what's happening here. So let me plot these points. Negative 3, 5, I'll show that in red. That's so far no different. Negative 2, 0. But here's where things change. Negative 1, positive 3. That's up here. Negative 0, positive 4. 1, positive 3. 2, 0. That's where the other one was. And 3, 5. All right, so what's happening here? Well, clearly, the graph of the absolute value of f of x is not the same as the graph of f of x. But we don't just want to connect the dots mindlessly here. We want to think what's happening. Well, essentially, when my outputs, when my y values of f of x were positive, the absolute value was doing nothing. It made no difference. Which means if I look at my parabola, anywhere my parabola is positive in terms of the outputs, my absolute value function will be identical. So what I'm drawing in red again is the absolute value of f of x. And those regions there, I'm just tracing over my original parabola, because in those regions there, the original parabola had positive y values, and the absolute value of a positive number is the exact same thing. It's only as soon as the parabola had negative y values that they became positive. So not only do I have these points here, everything I see below should get reflected up and look like this. And what you see in red is the graph of the absolute value of f of x. And what I drew in blue is the graph of just f of x. And again, everywhere f of x was positive, which means the outputs were positive or the y values were positive, the absolute value made no difference. The graphs I just traced on top of it. As soon as the absolute value, as soon as the original function or f of x had negative outputs, the absolute value of it it looked like a reflection, because the negative values of y became positive values of y. And there we go. And so this leads into the next lesson. But we see in red is the graph of the absolute value of f of x, or the absolute value of x squared minus 4. All right, and we'll stop there.